So welcome to lecture 5 of our chapter Moving Charges and Magnetism. So we begin with the two numericals based on the concepts taught in the previous class. So the first one is a closely wound solenoid 80 centimeter long has 5 layers of windings of 400 turns each. The diameter of the solenoid is 1.8 centimeter. If the current carried is 8 ampere, estimate the magnitude of magnetic field inside the solenoid near its center. So for this particular problem, we are considering that the length of the solenoid that is given is equal to 80 centimeter, which is equal to 0.8 meter, and the total number of turns. So the question is stating there are 5 layers of windings of 400 turns each. So 5 layers of winding of 400 turns each implies that the total number of turns is 2000. So the number of turns is 2000. The diameter of the solenoid is given to us as 1.8 centimeter. So this can be written as 0.018 meter. And the current which it is carrying I is equal to 8 ampere. So a current of 8 ampere is being carried by the solenoid. So if we calculate the strength of magnetic field, so the strength of magnetic field is written as mu naught small ni, where small n is turn per unit length. So if we put the value, then it is equal to 4 pi into 10 to the power minus 7. Small n, that is turn per unit length, can be written as 2000 divided by total length, which is equal to 0.8, into the current that it is carrying, which is equal to 8. So on calculation, we obtain a value equal to 8 pi into 10 to the power minus 3 Tesla. So this is equal to 2.512 into 10 to the power of minus 2 Tesla. So this is the correct answer for this particular problem. So let us move to the next problem. The next problem is stating a toroid has a core non-ferromagnetic of inner radius 25 centimeter and outer radius 26 centimeter, around which 3500 turns of a wire are wound. If the current in the wire is 11 ampere, what is the magnetic field? In the first part, it is asking outside the toroid. In the second part, inside the core of the toroid. And in the last part, in the empty space surrounded by the toroid. So if I draw the toroid which the question is referring us, then it is something like this. So there is an inner radius of the toroid, outer radius of the toroid, that is given to us. So, and the question is asking us magnetic field in the region outside and inside the toroid. So the answer to the first part and the last part is 0. There is no magnetic field in this region, which we have already discussed while teaching. So we are going to calculate the strength of magnetic field inside the core of the toroid. So we are considering that the inner radius, which is equal to small r, is given to us as 25 centimeter, which is equal to 0.25 meter, and capital R, which is the outer radius, is equal to 26 or 0.26 meter. The number of turns is equal to capital N, which is equal to 3500 turns, and it is carrying a current of 11 ampere. So if I calculate the mean length which we are going to consider, so mean length of the toroid, so then I am considering it as 2 pi capital R plus small r by 2. So we are taking the mean radius of the toroid and calculating the total length L which is it is offering. So it is coming out to be 2 pi by 2 0.25 plus 0.26 and the value is in meter. So from here we obtain a value equal to 0.51 pi meter. So if we calculate the strength of magnetic field now, so I can say that the strength of magnetic field B is equal to mu naught Ni, where N is turn per unit length. So small n is 4 pi into 10 to the power minus 7 and turn per unit length, that is 3500 divided by 0.51 pi into current, which is 11 ampere. So this is the strength of magnetic field which we calculate in Tesla, and it is coming out to be 3 into 10 to the power minus 2 Tesla. So this is the strength of magnetic field inside this toroid. So now we will be beginning with a new topic. So we are going to study the force on a current carrying wire. So we are discussing force on a current carrying wire placed in a magnetic field. So in order to begin understanding this, we are considering that the current carrying wire is basically designating a large number of electrons that is moving through this wire. So we are considering that a current carrying wire like this, having cross sectional area A, length L, is placed in the region of magnetic field B. So the magnetic field in this case is directed into the plane of paper. And we are considering that the electrons in this wire are moving in the downward direction. So they all are moving in the downward direction with a value equivalent to the drift velocity Vd, and hence we can say that the direction of current in this wire is in the upward direction, opposite to the direction of electron flow, that is I is in this direction. Or you can also consider that the positive charges are moving in the upward direction. So if we apply V cross B for this particular wire, we observe that the direction of force on this wire is in this direction. So the direction of force for this particular wire is in this direction. So in order to understand the value of force which is being applied, so I am considering over here that if Vd is the drift velocity, of the electron which is flowing in this wire in the downward direction, so I can say that the force on each electron can be written as F is equal to Q V cross B, or we can write as E V D cross B. So we are only talking about the magnitude right now. So the magnitude of force is going to be E V D cross B. So if I consider that the length of this conductor is L, having cross sectional area A, and the number of free charge carriers is n per unit volume. So I can say that the total value of force on all these electrons combined will become NEL VD into B. So we will get an expression like this: NEALVD into B, where N is the carrier charge density, A is cross-sectional area of the wire, L is the length of the wire. So I can say that the total force that is acting on it is equal to NEALVD into B. So over here, I can say that from the current electricity, I is equal to NEAVD. So I can put this as the value of current, and hence the magnitude of force on this wire can be written as ILB. So the magnitude of force on the current carrying wire placed in the magnetic field is equal to ILB. I am repeating the concepts back again. So basically we are considering that a current carrying wire is placed in a magnetic field B, and if we consider that the current is carrying in the upward direction, so I can say that the electrons are drifting in the downward direction. So the force on each electron is equal to E into VD into B. So now we are calculating the total number of electrons that is present in this wire. So if we consider that N is the charge carrier density, A is cross sectional area and length L, so the number of electron will be equal to NAL. That is, the force will become NEALVD into B, and hence the magnitude of force can be written as ILB, since I is equal to NEAVD. Now if I write this expression in vector form, then in the vector form we write it as F vector is equal to I L cross B, and we can also write it as F equal to ILB sin phi. So these are the ways by which we write this particular equation. The force is always perpendicular to both the conductor and the field, and the direction is determined using Fleming's left hand rule. So we determine the direction using Fleming's left hand rule. So according to this rule, our index finger is representing the direction of magnetic field, the middle finger is representing the direction of current, and our thumb will give us the direction of force. So if we align the two fingers in the direction of magnetic field and current, then our thumb will align itself in the direction of magnetic force, such that the force F vector is perpendicular to the length of the conductor and magnetic field. So now we are considering what if the wire is irregular in shape. So if the wire is irregular in shape for an irregular shape conductor, so if we consider that it is not a straight wire, so I can say that we can divide this wire segment into infinitesimally small length, each of length dl. That is, if I consider that a wire like this is there carrying current I, so we are considering that a wire like this having end A and B is carrying a current I, and it is placed in the externally applied magnetic field B. So in order to consider this, we consider a small wire segment which is of infinitesimally small length dl, and due to this segment we consider that a force dF is acting on it, and its direction is given by IdL cross B. So if we integrate this expression along the entire length of this conductor, so we will attain something like this: F is equal to I integration of dl cross B, and we write it in this sense that F is equal to L naught B vector, where the L naught is the length of this conductor measured between the two ends. So if I join the two ends, then this is the length L naught. So we replace this equation with this L naught, and we write the value of force F, which is equal to I L naught B. So basically, if the wire segment is irregular in shape, then the effective length segment for the calculation of force is the shortest distance between the two ends of the wire. So now we are calculating the force that is acting between two large wire placed parallel to each other. Force between two large current carrying wire placed close to each other. For this, we are considering that two wires placed close to each other are carrying current I1 and I2 and are separated by a distance d. So for this particular arrangement, the first thing that we are going to calculate is the magnetic field due to wire A on the wire B. So I am writing magnetic field due to wire A on B. So we write that the strength of magnetic field due to an infinitely large wire is equal to mu naught I upon 2 pi d. So this is going to be the magnetic field along the length of this current carrying wire I2. So if I select a portion of length somewhere in the middle of the wire, say having length L, and the direction of magnetic field due to this is in the inward direction, having the strength mu naught I1 upon 2 pi d, the direction of magnetic field can simply be determined using Maxwell's right hand rule. So if we place our right hand in the direction, right hand thumb in the direction of current carrying wire I1, such that our thumb is pointing in the direction of current I1, then our palm will be in the inward direction near the wire I2. So I say that the magnetic field is directed into the plane of paper. Now if I apply the value of force, so the force that is acting on this length L on the wire B is equal to I. So the current which the wire B is carrying is I2, magnetic field, and the length L. So this is going to be the magnitude of force that is going to act on this length segment. If I check the direction of force using Fleming's left hand rule, so I say place your index finger in the direction of magnetic field, that is in this case directed into the screen, your middle finger in the direction of I2, that is upward, so your thumb will be pointing in the direction of I1. So I say that the force when the two wires are carrying current in the same direction is attractive in nature, and from here I can write that F by L for this length segment is equal to mu naught I1 I2 upon 2 pi d. So the force per unit length expression for this wire segment is equal to mu naught I1 I2 upon 2 pi d, and the notable fact is that if two wires are carrying current in the same direction, they will attract each other. Two wires carrying current in same direction attract each other. While two wires carrying current in opposite direction carrying current in opposite direction repel each other. So since these two wires are carrying current in the same direction, they are going to attract each other. Let us deal with a problem. So the problem is stating two long and parallel straight wires A and B carrying current of 8 ampere and 5 ampere in the same direction are separated by a distance of 4 centimeter. Estimate the force on a 10 centimeter section of wire A. So for this particular wire, we say that the two wires that are carrying current, that is I1 and I2, is equal to 8 ampere and 5 ampere respectively, and they are separated by a distance of 4 centimeter. So I can say that the force per unit length on this wire segment is mu naught I1 I2 upon 2 pi d. Now the question is saying to calculate the force on the length segment of 10 centimeter, and hence I can say that the magnitude of force F is equal to mu naught I1 I2 upon 2 pi d into length L, which we can calculate as 4 pi into 10 to the power minus 7 I1 I2 into length L upon 2 pi, and the separation is 4 centimeter. So this will give us the value of force that is acting between the two wires, and the value is coming out to be 2 into 10 to the power minus 5 Newton. So if the two wires are carrying current in the same direction, then the force is attractive in nature. So next we move on to understand the concept of torque on a current carrying loop placed in a magnetic field. So we are understanding torque on a current carrying loop on a current carrying loop in magnetic field. So in order to understand this concept in a better way, I am drawing arrangement like this. So I am considering that the two poles of the magnet are facing each other. That is, this is behaving like a north pole, and this section is the south pole. And over here, in the middle of this magnetic field region, I am placing a current carrying coil which is carrying current like this. So we can connect it using a split ring, and it will look like a DC motor arrangement with carbon brushes attached. So this is the source of current with a battery and a rheostat attached. Key K. So the direction of current is like this in this magnetic field. So the magnetic field is directed from the north to south direction, and we are marking it in red. So this is the direction of magnetic field on this current loop. So if I consider that this is the length L of the loop and the breadth B of the loop is B. So now if I calculate the value of force which it is going to experience due to the magnetic field B. So I am drawing one more diagram over here for this current carrying loop, and we are naming it as PQRS. So this is PQRS which we have drawn over here. So now the direction of magnetic field is towards right. The direction of magnetic field is towards right. The current in the wire PQ is in the upward direction, that is like this, and in RS it is in the downward direction. So in order to determine the force on PQ and RS, if we use Fleming's left hand rule, so the index finger is in the direction of magnetic field, that is towards the right of the screen. The current is in the wire of PQ as marked over here, and you will find that your thumb is pointing in the downward direction. So I say that the force acting on PQ is in the downward direction F. Similarly, if I find the direction of force on RS, so I say that the magnetic field is towards the right of the screen. Your middle finger is pointing from R to S and your thumb will be pointing upwards. So in this case, the force due to the current carrying wire is upward. So due to this two equal and opposite force, a torque is generated on this coil and it will start rotating in this sense. So a torque is generated on this wire segment and it will start rotating in this sense. So if I consider that this length is L by 2 and this length is L by 2, so the first thing which I can write is that the magnitude of each force F that is going to act on length PQ and RS is going to be equal to I length B magnetic field capital B. So ILB, the value of force is attained as IBB, and hence the net torque which is going to be experienced is going to be L by 2 into force F, which is IBB, times 2, and we attain a value equal to ILB into B. So if there are n such turns of loop, so I am writing, if there are n such turns of loop, n such turns of loop, then I can say that the torque is equal to In L into B, where this is area of the coil, and hence I write it as torque is equal to INAB. This expression INA is written as magnetic moment capital M vector cross B. So this is the expression of torque on a coil placed in a magnetic field having magnetic moment M vector, where magnetic moment which is M vector is equal to INA. The direction of magnetic moment due to a current carrying loop due to a current carrying loop is determined by curling our right hand in the direction of current, by curling our right hand in the direction of current in the loop, and our thumb will give the direction of M vector, and our thumb will give the direction of magnetic moment M vector.